they pointed out a very interesting property of superstring perturbation theory, which I was sure at the time would have an impact on the field. But it didn't. I recently did a citation search for their paper, and it has very few citations. And nobody did anything significant with it. And the authors of the paper are probably, well, at the cost of being a little bit melodramatic, I feel that the authors of the paper and me might be the only ones who paid attention to it. So I think it would be a shame if we all retire and the paper gets forgotten. So I kind of would like to do something with it. Yes?
Have you had occasion to think about the Vasilyev invariance at all?
Well, I'm worried that that isn't the right question for this audience. The answer is not on purpose. But once a colleague, Lev Rosansky, and I discovered a new way to construct a quantum theory, some people call it Rosansky-Witten theory, that generates some of the Vasilyev invariants. But I can't think of anything to say about it for a general audience, so I think I'll stop. Any questions? Yes?
It's my understanding that 30 years ago, string theory, people thought might be the theory of everything.
Yes?
Do you still feel that is that the case? And
It's-
to prove it physically?
It's definitely our best shot. It's our only real shot. And we've definitely discovered a lot of exciting ideas that go way beyond what we'd understand today if we hadn't had string theory. For example, the kind of mathematical physics related to Kovanov homology. That's miles away from physics, but it's an illustration of the power of the ideas. We wouldn't have that except because of the way they show up in string theory. Personally, I think string theory is on the right track, but it might be younger people who will have to decide that later on. Yes?
I wasn't exactly clear on exactly the context of the reference to inflationary theory.
Yes.
So maybe I misunderstood.
I was asked, okay. The answer to a question I was asked about magnetic monopoles is that I spend my time working on theories that only make sense if monopoles exist. But they haven't been discovered.
Right.
So you can ask your question in a moment, but I just want, since my answer apparently was unclear, I want to elaborate on it slightly. The answer to the previous question. I perhaps extrapolated slightly from the question David asked before, but a semi-compelling explanation of why the monopoles haven't been seen if they're there is the inflationary universe, which in fact was invented precisely to reduce the abundance of monopoles in the real world. That might be the right interpretation, although it's a frustrating one. It would have been better if Alan Guth had reduced the abundance of monopoles to a manageable amount. But unfortunately, he overdid it. Anyway, what's your question?
Well, just that I read that Roger Penrose just came out with a paper that said that that's kind of not exactly debunking, but saying he doesn't believe in inflationary theory. But I was just curious whether that was something you had seen.
All big theories have their skeptics. Yes?
Speaking of which, can you comment on the book Trouble with Physics? Lee Smolin?
Well, I can't comment very usefully because I haven't really looked at it. But as I said a moment ago, all big theories have their critics.
Exactly.
Yes?
In the example you were working through, where you assume a three-dimensional space-time,
Yes.
where you talk about
Yes.
polynomial associated to the path
Yes.
of particles in space-time, it sounded as if the polynomials would only be defined if it was genuinely a knot, so if it didn't actually cross itself, intersect itself in a three-dimensional space-time. But I don't see why it shouldn't do so. If you allow the paths to go back in time, why mightn't they pass through the same point in space-time?
Well, they can pass through the same points, and then you run into a phenomenon. Okay. For example, Newton had the 1 over r squared force law, so if particles get close, there's a strong force. you have to calculate that force. It changes the answer. So two strands can pass through each other, but when they do, the quantum answer changes. There's a simpler theory when they don't pass through each other, but it makes sense. Your question makes perfect sense. It has an answer, which the quantum theory will give.
So the knot polynomials are defined even for a path that does cross itself?
They're not usually called knot polynomials, but there's a more general thing you can define when they do cross each other. You get a different answer. A space-time history that is self-crossing is different from a knot. So it can have a different answer, and it does. I even wrote a paper about it once. Any other questions?